Good afternoon. Today's topic, Cognex online training session will be our DVT color tools. So we will go through the whole range of color tools in the Intellect environment for DVT cameras, which include pixel counting, color monitoring, and color identification tools. So we'll go through each of those and have a little introduction on our colored cameras and color in general. So for color cameras, you'd see the Legend 5XXC type products, which would include the 545C, the 552C, and the 554C. Basically, the way that grayscale, a CCD, a color camera is used is there is a CCD with a filter on top of the CCD, and each pixel on that CCD identifies one of the three color, basic color elements, red, green, or blue, and identifies the intensity of that particular wavelength on that particular pixel. So that means that when you see something like what we're seeing here, this three color filter, we see that a particular pixel only gets from the original image, from the scene, one of the three values, red, green, and blue. So the other two must be interpolated or calculated from the neighboring pixels that obtain a value of that other color that's missing for that pixel. So for example, in this central blue color here, or pixel which obtains a blue intensity, the green value for that particular pixel will be interpolated or calculated based on the four neighboring green pixels, or pixels that obtain the intensity values for the color green from the scene. The same with red. The red value for this particular pixel will be a value that is calculated from the neighboring pixels, which obtain that red value, intensity value from the scene. Why is this important? This is important because these interpolations make it less accurate to perform precision measurements on a color camera. So if you need to do precision measurements or a measurement application, you should not use a color camera unless it is absolutely necessary, because your accuracy will be reduced from the very start just based on this interpolation. So each pixel doesn't really have a way of obtaining red, green, and blue directly from the scene. So when we talk about color, specifically the red, green, and blue color space, we can think of a three-dimensional space, orthogonal space, like the one shown here, where each of these basic colors, red, green, and blue, are in an axis. So from there, we can pinpoint a location on these three-dimensional space and obtain a red, a green, and a blue value for that particular pixel in this RGB color space. The other complementary basic colors are cyan, magenta, and yellow, and they're usually used in the optical density color space, and we will see why later on. The grayscale line is a line that goes from 000, absolute dark or black, to 255, 255, 255 for red, green, and blue, which would make perfect white. Um, the pixels are actually have a value from 0 to 255, but to simplify uh, things, we actually give a scale of 0 to 100% intensity for each pixel. And this is also true for the grayscale cameras. Instead of 0 to 255 grayscale value, we actually have a 0 through 100%. There's no question. So that's a color cube, and RGB is usually gives you um, basically a pinpoint location. But really, when we learn a color, we usually do not learn a single point in this three-dimensional space. We usually learn a group of colors around, let's say, the average color in the scene or in the field of view or the region of interest of the tool. And that's what's being shown here. There's a normal color variation based on uh, the properties of the part that is reflecting the light, based on variations on the light itself, based on um, environment properties or conditions, and also based on the interpolation calculations that go on uh, based on that CCD. So because of all that, even colors that are supposed to be the same, or a part that has supposed to have a solid color, not every it's very unlikely that every pixel in that color in that part, even if it is a single part and a single solid color, it's very unlikely that all the pixels would have the exact same red, green, blue combination of values. For that reason, for that normal variation, because of that normal variation, you would have a learned color that's actually not a single point in the red, green, and blue three-dimensional space, but rather um, a group of pixels that include a little bit of the standard deviation, so that we include some of that normal color variation. So what you end up learning is something like a small cube based on the standard deviation seen in that learning image for the three different red, green, and blue channels. Um, so besides that point, there are three color parameters for these red, green, and blue values for this three-dimensional space, color space. These are color parameters that are pretty standard across the industry, and they can be modified to include more or less colors into your learned color, the model color. And these are the sigma factor, the matte line, and the highlight line. The sigma factor would increase or decrease depending on how you modify this factor. The number of colors around the average colors that gets included into your model that you're learning. So basically, and we'll see it in a subsequent image, but if we go back here a second, it will basically change the size or the volume of this cube here. So based on the amount of either increase or decrease on that sigma factor, you'd basically increase or decrease the volume of that cube, including more or less colors around that average color. So that would include colors that are very similar, but that are not necessarily of the same color content, but just darker or lighter. To include things like that, that is, colors that are the same uh, red, green, and blue proportion, but either a little darker or a little lighter, you'd use the matte line. That matte line is a line that connects the color in three-dimensional space with directly with the 0, 0, 0 point. So if we go slide further here, we will see this little cube here. If we have the internal black cube there as our initially learned color, if we increase the sigma factor, we can increase the volume of that cube in three-dimensional space, making it similar to this green color here that we've represented, um, with which we represented that group of pixels that are learned. The same matter, this line here, which is actually obviously not a line because it's like extending this cube in both directions, that is the matte line. And the matte line will again include colors of the same red, green, and blue proportion, but they would be either darker if we go on the dark side of the matte line, which is the one that goes from 0, 0, 0, or perfectly black, to our color in three-dimensional space, or on the light matte area, which would be from that object all the way out until one of the colors saturates, which in this case happens to be red, and then it'll crawl along that wall, going to 255, 255, 255, which in this case it's represented as 100% white. Basically, it's perfect white. So from our point or our group of points or cube in space 2, 0, 0, 0, that's a dark line, and if we want to include colors that are darker in shade but that the color content is the same, red, green, and blue values change proportionally darker, then we increase the amount of advance that we go through the darker side of the matte line to include those darker colors. If we want to include lighter colors of the same shade of color, same color content, then we include the light section, or we increase the light section of the matte line parameter. Finally, the highlight line is basically include areas that are close to specular reflections or saturation. So we will see a case of that when we go to our workshops, to our sample. But basically, it's this line over here where the color D is included. So if we have this as our original color and we increase the amount of highlight that we allow, then we start including colors in this direction, which might include D if we increase that highlight line percentage quite a bit until it reaches one perfect white. So this is an example where we have a learned color, and if we go towards the darker side of the matte line, you see that they stay proportionally the same, but darker in general, so lower intensity. The opposite with a brighter matte line. If we increase, here we're increasing it proportionally, so it's basically the same color but a lighter shade of the same color, and that would be on the bright or the light side of the matte line. This saturation matte line section is basically after one of the colors has saturated, in that case red, you'd see the matte line crawl along that wall towards white. So if we want to include the color C, we would include increase the lighter side of the matte line enough so that we can include C in there. So you see one of them is saturated, so the relationship is no longer exactly proportional for that particular color that has reached saturation, but the other one still maintain the same proportionality. Finally, D, as we mentioned before, will include the highlight line. and the point E right here is not included in any of them. If we wanted to include the color E, we would see later on that what we can do is learn that color separately and then merge them together. We'll look at that later on. Now, why do we need to know this? We need to know this sometimes if we are using, we will see later on that we have two main methods of learning colors, a single color learning method and a multicolor learning method. If we're using a single color learning method, we would basically learn an average color plus a little bit on each side of the red, green, and blue three-dimensional space in order to include some of that normal color variations that we mentioned before. So that way we have more control over that single color that gets learned if we start manipulating these parameters. We'll see later on that sometimes that's not very practical. It takes some trial and error to get exactly what you want, and things that you might be able to accomplish much more easily if we use the multicolor learning method. So as an example, if we look at the color histogram of an orange, we'll see something like this in three-dimensional space. Now, it's possible that what we end up learning is actually only the strongest point, so maybe around this point, which is the color that is more commonly found in that orange, and then include a little bit around it, as we said before, to include some of that normal color variation. If we include the matte and the highlight line, we start including things that are similar in shade, but going through black or white, and also towards things that might include specular reflections on that orange. We see a couple of areas here where colors have saturated. If we want to increase the area around it, so more colors, these will be colors that are not the same color content, lighter or darker, but rather different colors are together, but very similar to what we learned initially. We would use we would increase the sigma factor. So this is an exaggeration to illustrate that fact. So this way you can manipulate that color that you learned. And again, this is available when you use single color learning. In this case, you have one soft sensor and one particular color. So you basically, the way you learn this is the sensor automatically, the tool automatically learns that color when you first draw the tool. So when you're drawing the tool, what you're drawing is the learn region. So you draw it around the color or inside the color that you want to learn, and the tool automatically learns that color. Once that color is learned, you can use these values here to change those parameters. If you want to include the map areas, the highlight areas, or increase or decrease the sigma factor to change the actual color values that are included in that color model that you just learned. Now, you could also use single color learning, but instead of using one single color, you may actually learn multiple single colors. So, for example, if you're doing a classification, if you're trying to solve a classification application, you would do something like this, or you could do something like this, where you learn single colors and maybe play around with those with the properties of each color, and have multiple of those single color learns. So if you want to learn a new color, you just click that learn a new color. If you want to change values for the sigma factor, matte area, and highlight area for each of these, instead of using this global section in the training tab or training page, you should go individually into each of those colors and click the properties box there. This is in the Manager tab of the color. We'll go to Intellect in a little while and show you what that all is. But uh, these global these are global parameters, and they if you want to affect each of these individually, you should use that should bring up the properties for each specific color. So what you would do in the Manager tab, select one of those colors and click on Properties, and there you would be able to change that sigma factor matte line or matte areas and highlight line. Now that's one way of doing it, of learning a color model. A different way of learning is using this multicolor learning process. And in this case, we could have one or several of these learned in a single soft sensor or tool. So at this point, is not that much different from what we have seen. The difference is that when you learn a merged color here, a multicolor, when you do multicolor learning, you're actually learning individual color values that are present in that in your region of interest, in your learning region. Now, in this case, the colors that are learned are actually pinpoint locations in that three-dimensional space. We just look through the region of interest, and if we see a value that is repeated in that region of interest more than this threshold number of pixels, which the default value is 10. So if you have a region of interest and you're learning a merged color here, and in that region of interest we find a particular exact RGB combination of values, an exact color, more than 10 pixels, we would learn that value. But in this case, because it's multicolor, we actually will learn all those colors, all those exact RGB values of colors that are present more than 10 times, and together we would put that into a color model, which is what gets learned here. So in this case, we're actually not using any standard deviation, any normal color variations to artificially include some of those values as we do when we use the single color learning. Remember that cube in the three-dimensional space. So in this case, in multicolor learning, we do not have something like this where we would include a cube. We actually have pinpoint locations that if present, if that value is present more than that threshold number of times, 10 is the default again, we would, let's go back to that one, we would add that specific value to a color model. So our color model is not really a cube in space, it's just a group of individual pixel values that are learned, and together they form a color model. In practical, for practical reasons, this is most of the time the choice when we're doing pixel counting color applications, be it for classification or identification or presence-absence applications and so on. So in this case, because we don't have to worry about sigma factors or matte areas or highlight areas, we just learn all the colors that are present, then that's practical. Now, on the other hand, we need to make sure that throughout all our images that we're trying to inspect in this application, we have pretty much the same color values for our part. If we anticipate our part to sometimes get a little darker, sometimes get a little lighter, and we did not learn those exact values, we have two options. If we know that that is a normal variation and that is going to be there all the time, we can actually add those individual absolute color values to our C2, our color that we previously learned. So that's one advantage here. We can add more individual pinpoint locations in that three-dimensional RGB color cube as we go along. Now, if we cannot predict what those would be, so we cannot add, we cannot go through a training phase where we just keep adding everything that is possible, because if we don't know all the different variations, then, but those variations are similar in its RGB value to a value that we want to learn, then maybe the best option is to go with single color, because in that case we could increase the matte area and grab values that are similar in color but darker or lighter shades of that color. If we don't know exactly what those values would be, but we know that they're going to be a little bit darker, a little bit lighter, then maybe that's the way to go. So those are the two main differences. In single color learning, we have the ability to change these parameters, color parameters like sigma factor, matte areas, and highlight areas. While in multicolor learning, we don't have that fine control over the color that's learned, but it's a much easier process, and we can keep adding or removing areas. So we're going to show a couple of examples for those cases. We can also learn many different colors. So every time you want to learn a different color altogether, let's say it's a classification or an identification application where we need to have different colors altogether, we can learn several what we call merged colors, and then add or subtract from each one of them, depending on the normal variations for that specific part. And those will be added to the managed list, to the list on the manager tab. A merged color appears with an asterisk after it. That means that it's locked and we cannot change its sigma factor, matte area, and highlight area. We can also have individual single colors and merge them together, and at that point the color will also appear locked. All right, when we open the properties for a multicolor learning, we'll see that the color is locked because it's a merged color by default, because we grab a whole group of individual locations or individual colors in that three-dimensional color space, RGB space, and merge them together under one name. That's why it doesn't make much sense to include to change the sigma factor, matte area, and highlight area. So those are locked. You cannot change those. What you can change is that threshold. For example, if you have a very small part, you might want to decrease that threshold so we include all the different individual colors there, because if we have a small part, we may not have many colors that repeat themselves more than 10 times in that region of interest for 10 different pixels. So if we have a small part, we can decrease the threshold. If we have a large part and the color is not very consistent, very solid, we don't want to learn every single value of RGB in that very large part, so we might want to increase the threshold and only include the individual RGB values that are most commonly present and most representative of our part. So we might want to increase that threshold. So again, this threshold is not an intensity threshold. It's a threshold in terms of pixels of that individual value in terms of RGB intensities that we are learning. Now for both single color and multicolor learning, we use the digital relearn options. In digital relearn, it's a way to automatically, through physical I/O or discrete I/O or Ethernet I/O, but through one of our virtual I/O or physical I/O values change the task that the learning task that is going to be executed the next time the camera is triggered. So this is a good way to automatically learn colors based on let's say a change of parts or a change of shifts that are inspecting different parts, different color parts. And usually you do this for an application where you cannot predict all the different variations of colors that you or models that you need to learn. If you can in fact predict it, then it's better to just learn all of them and then inspect with all of them learned at the same time to get an idea of the number of pixels that match that color, and if it's a classification application, which of our color models is closer to our current part. But if we cannot predict all those combinations, then we can use these options for digital relearn. So what that means is when you send the signal that you specify here, then the camera on the next inspection can do one of these options. They are self-explanatory in general. So you have an option to learn one color and append to the color that's already there. You can remove all the existing colors and learn one. In that case, it would be a single color learn as opposed to this option which says remove all and learn merged, which would be a multicolor merging learn operation. And then you can also add or remove to the multicolor learning method. So you can do all that through the digital relearn option. So again, that would be in cases where you have, it could be either a case where you've learned the color, but then you've detected, or you can foresee that there's going to be a variation, slight variation of that color model. Then you can either remove it and learn a new one, or you can just append or add to that or remove from that color model. So what would you do remove? You would execute a remove operation if you have a particular color that is common to all your parts or a few of your parts. So you want to remove them from each of those parts so that that commonality does not throw the camera off when it's trying to decide, let's say on a classification or an identification application, which of the model is being presented to the camera at that point. Because if all those models are totally different, then they don't have anything in common, then it would be much easier for the camera to distinguish between them. So again, add would be used to add different variations of that multicolor learn model, and remove would be used to remove some color content that may be common to other tools. So color basics. As the conclusion for the pixel counting tool, we have that first of all, you need to white balance the system. This is something that we didn't mention before, but we're going to go through now when we connect to a live camera here. And it's essential that you do this. You need to white balance the system. Different lighting sources will have different color content. So you need to do this every time you change your lighting as well, especially if you change light source. But you may also need to do it if you change your light position or angle, if you also have other lighting involved, like for example ambient lighting, because the new combination based on the angle or location may give you a different color content for illumination in general. So you will have to white balance the system when you change your lighting setup, and that's very easy to do, and we can go through that as well. Also, another point is that pixel counting tools or soft sensors can also be used in monochrome systems. And that's because our pixel counting tool is exactly what is called, and it basically counts pixels of a certain intensity. This intensity could be grayscale intensity, or it could be a particular RGB color model or group of colors. So this could also be used for, let's say, presence-absence applications um, in monochrome systems as well, where we're looking for an area of a particular grayscale intensity. We can also use it and pass it to a filter tool, and we will look at that in just a second, so that we can use it as a thresholding value or an image processing operation. So let's go through, let's go to Intellect and show some of what we've been talking about. All right. So in this case, let's go and start a new product. You'll see that right now the camera is actually white balanced. It's actually overexposed. But you can see we have a white piece of paper, and it's you would see it as a relatively consistent gray value throughout the region of interest. If we change the illumination, in this case I'm turning on the white LEDs, the front of the camera, you'd see that because the content of that light source is a little bit different, now our image is very blue, and that's because basically white LEDs are blue LEDs, are modified blue LEDs with a phosphorus coat top of it. So if we want to use this lighting technique, change it, or lighting source, then we need to do a white balance operation, and that is done using this button of the toolbar. If I press that button, get something like this. Notice that it's very important that we have even illumination, not just because that is a base of that is very important in terms of getting a good image, but also because the white balancing operation occurs in the center of the image. You can see that area right there. We press the auto white balance, and we see an image of a white piece of paper that is now kind of white. You'd see some changes because we don't have even illumination, and the gain was only adjusted in the middle, and now we have some ambient lighting. Also, on the edges of our tool, we see that there's higher red and green content than there is for blue. You can see the values right here at the bottom toolbar as I move my cursor through the image. While in the center of the image, they're all around the same value. Outside, you see the blue content be a little bit lower. When I go back to using our actually office lighting here, which is not good for an application, but in this case, for demonstration purposes, we would use that. And I'm going to go back, and you can see that the blue content is lowered. That's because we had to change the gain of the blue channel to adjust for the light for the white CCD when we did the white balance. So we know we use now a different lighting source, and you'd see that you need to do auto white balance again. So I'm going to do white balance here, and we get, again, a consistent red, green, and blue value. All right. So I'm going to go back now to an emulator and show some of the basic um, operations of the color tool as we have talked about in this class. So the pixel counting tool is under the counting group, and again I'm going to choose in this case rectangle. Choose anything there, and I'm going to learn this color. And you notice now that we learned this way of learning, and again I drew the learning section first, train section first, and it already learned a particular color. And that's C1. We can change the name of it if we double click or click on properties, change the name of that, call it orange. Hit OK. Now in this case we've done a single color learn operation, and we in this case have learned a few of those values around it. So if we want to, we can do two things here. We can either add to this color. If we, you notice that when I clicked once on the tool, let's do that again. Now I also get an extra toolbar here in the video display that gives me the option of learning new colors from here instead of using the tool parameters. This is basically a shortcut. If we use the add or remove buttons, basically what would be using, go to the training tab here, these add or remove buttons here, which would make this learn color a merged multicolor model now. So right now it's a single color that I've learned, but if I click here and I'm going to move this to this other region and try to include other areas of the color. Now I have included more color values similar to that orange. Now I have locked this this color. So this is a very simple way of including different color or including different color contents, but of a similar intensity. So I just move around. That's why I said practically this is a very simple and easy way of adding colors. Now in this case we are assuming that everything that we add here will be pretty much consistent through the rest of the images. If it's impossible to do that, to foresee that, then what we can do is learn a single color and change those map areas and so on, which we will do next. We'll do next here. But this is a very easy way of learning a specific color model that is formed from different exactly red, green, and blue pinpoint locations in our three-dimensional space. We can change that threshold so that we set it to 1. We basically learn every single color that is present. When I say color, I mean RGB combination that is present in our learn region. So if I do add here, basically I learned everything that was there. You see the image marking, basically we inferred the color so that we can look at that. We can see what areas are being considered as part of that color model. Now if we go through the sequence of images, we should see all those orange parts being selected there. All right. Now if you want to, we can delete this. And we can go back to training and include larger area here and learn a single color, as we did before. Now let's change, if we change the sigma factor here, or if we change the matte areas, for example, now we have enabled the dark side and the bright side of the matte area. We've included about 50% of the this means basically halfway from our object, our color in the three-dimensional space to the 0, 0, 0 point. So halfway through there, we've included everything. The same thing on the bright side. So if we reduce this a little bit more, we basically only include just a little bit on that line that goes from our point in three-dimensional space through black. So you notice a lot of the other pixels that we had included before in this red area disappeared. So we're not counting those anymore. Now these areas here are probably part of the white of the brighter side. Change maybe that through by reducing our brighter area, or by reducing our sigma factor. The problem in that case, this color is actually very similar, so reducing the sigma factor got rid of some of those, but it also got rid of some of our other colors. So you see how it can become a little bit of a challenge to through trial and error kind of include all the variations that we want. If we include the highlight areas, we start including the white pixels. So now all the white pixels are included. We don't want to do that, definitely, because our background is white. So everything that is a specular reflection, or looks like a specular reflection of white, then will be included. So now we have two choices if we want to include some of these. We can either manipulate further the matte areas and the darker and brighter side. Try to include brighter shades of the same orange color. That's not helping us much here. Or we can actually do a multicolor learn. So right now, at this point, if we add to this color, we will actually convert this model, which is a single color model, to a multicolor model, and we will learn based on this threshold here, other color. So if I add that, now I've switched over to multicolored learn, so that's an easy transition. And I've added all those colors. In our Manager tab, we would see that that color is now locked because it's a merged color. That means that we couldn't change the sigma factor matte areas in highlight areas. Also notice if we have a color that's been selected here, we would get that area here delimiting all the pixels that are included in that color model. If we want to get rid of these pixels that are part of another object, so we don't want to include those in the orange color because those are part of the red color, even though it looks a little orange there because of the illumination, we can click on the Remove from C2 button. So anything there that matches our threshold, which means every single color in this case, because our threshold is 1 pixel, we will get removed from our model. So in this case now, we may have gotten rid of some of the pixels here on our part, but on the other hand, we have more separation now from other groups. We have some pixels here that are getting included. I delete those two, and now we start getting rid of. And you can see that some of these are like a dark yellow as well. That's why they were being included from that from that yellow part. Okay. So this could either be a counting application. This could be an application where we want to count individually how many of each of those colors we have present, in which case right now we have an orange. If we want to count the yellow ones, we would need to add a different tool, because if we add um, if this were a classification or identification application, then we could actually learn all the models under the same tool, but then the tool would come up with a single result, which was the closest color to the current color that the camera is looking at, to the current part. But if we have something like a counting application, we want to count them individually, then we would need to create different pixel counting tools, one for each color model, so that each of those tools have a separate output and will allow us to count either the number of pixels or do a blob extraction. So that takes us to the next topics, which is, let's say that this is not a simple counting or identification application or classification application, in which case we could use just single pixel counting tool, learn several ones, and then the result will be how many of those pixels belong to the most dominant color, which in this case is C2. We can change that to orange, and it tells me the number of pixels of that color. Let's say that we want to do a blob extraction, and we want to actually count the number of objects. So in this case, we're only counting the number of tools or pixels, number of pixels of that color. If we want to do that, then we need a way to move this information, this color information, and share it with another counting tool. Could say, for example, a blob tool. So to do that, we need to use a pre-processing filter. So I'm going to draw a pre-processing filter across most of the image. And say this call this filter. And under options, I'm going to choose thresholding, color, and then I'll use tool 1, C2. Hit apply, and everything gets blocked except for those colors there. We can do a little bit of morphological operations to dilate all those, so that we basically join all those pixels. Some of these pixels are kind of orphaned, and they're floating in space. We can do that in our blob tool. So we can do a counted area. So right now we've created another image through. So what the filter tool does, it creates a new image based on an input. And what is that input? The input is that color information from the pixel counting tool, and for that specific color within this pixel counting tool. So right now we've just created a new image, and this counter or blob counter under image reference will use that filter, actually reduce my region of interest so that it's within our filter. And now the blob tool is counting a few blobs, and we can do some morphological operations to include some of that, or expand and dilate the blobs. We can increase the minimum size, say to 500. In that case, we only get the main two. Go to our selection tab, we see the two numbers. So now we're counting 2 blobs. So this is a way to share the colored information from one tool to the next. If I go back to our presentation here, we have a couple slides on that. Basically, this is what we just went through. We want to link this pixel counting sensor data, we use that filter tool. So this is what we used. And then if we want to pass that along, basically what that does, it creates an image, and that image can be an input image for other tools, like we did for our blob counter. This is a way to extract information based on color and do some thresholding and create new images based on that color information. And it's a way to pass that color information along to other images, to other tools, so that it can be used for other purposes, as in this case we used for counting blobs. So another color tool that we have, so we've looked at pixel counting. And pixel counting can be used again for presence absence application. We want to make sure that a certain number of pixels of a certain number of colors are present in our field of view, our image. We can use it for classification or identification if we have a sequence of or a series or a number of color models that we've learned. Then we can learn multiple of those models within the same part or within the same tool, and then have the tool tell us, based on an image and a current image, what is the most dominant color, which one of the color models that we learned is the one that is being detected at that time. It can also be used for counting, as we just saw, by just extracting the information and passing it along to other images to other tools through the filter pre-processing tool. If we want to do a color monitoring application where we want to monitor the exact value, red, green, and blue value, color value of a part, we should use a color monitoring tool. Color monitoring tool is a more accurate tool from the point of view of the number of colors that it identifies, but it's not suitable for the other type of applications that we've talked about, because especially if we have parts that are not very consistent, that they don't have solid colors that are very consistent. The reason for that is that the color counting tool, the color monitoring tool, identifies the average color in a region of interest. So the average color in a region of interest has to be very consistent from part to part, so that we can distinguish, let's say we're using this color monitoring for color verification. How close am I to the desired color, to the color that I learned, so that we can use it as a closed loop control of painting processes or some other type of monitoring processes, where we need to figure out if our color deviates from the color that we learned to a certain extent, then we need to know, or above a certain limit, we need to know. So for that, because only the average color is learned, then the average color needs to be very consistent from part to part. And this is what we want. That's why we want the color monitoring tool in this case. Color monitoring tool uses 16.7 million colors, basically a 24-bit color, whereas pixel counting only has about 65,000 colors. So it can detect smaller changes in the color content than the pixel counting can detect, and that's why we use it as a color monitoring tool. It can be used as a color identification as well. It can learn multiple models, present it apart, and have the tool tell me which one is closest to and by how much. This can be used for color identification in cases where colors are very close to each other, because exactly what we mentioned before about the number of colors that it can distinguish between and it can detect. So if we have an identification application where we have very similar colors, It might be better to use color monitoring than pixel counting, but again, it would have to be a case of a solid color and a very well-lit part, lighting that's very consistent throughout the image and from image to image as well. So if we have um, those requirements met, then we can use color monitoring for very precise color identification. This tool doesn't have two different regions as we saw in the pixel counting, a learn region and a search region, or an inspection region. It actually uses the same region for both because, again, it detects the average region, the average color in that region, and that's exactly what it learns, and that's exactly what it detects at inspection time or run time, if we will. So in the color monitoring mode, we want to know how close am I to the desired color. So it uses, it may use different color spaces. The default one is red, green, and blue, and we'll talk about color spaces in a minute. But once we have the red, green, and blue model learned, then the result from that point on, the output of that color tool will be the distance, the difference in three-dimensional space between the learned color and the current color, the actual color that is being presented to the camera at that point. You would have the individual X, Y, and Z. The reason why we say X, Y, and Z here instead of just red, green, and blue is because these could be other color spaces instead of just the red, green, and blue color spaces. So it could be LCH or LAB, and we will look at that in a moment. And also a total difference from one point to the other. Again, the color, the difference in terms of number of colors is important in this case because we're going to get very fine discrimination between colors. So this is what we were talking about just a minute ago in terms of color spaces. Red, green, and blue is the main color space. This is the color space that the camera acquires images with. It's a CCD with red, green, and blue values. We have other color spaces that are available. These color spaces, is important to know, that are always calculated from the red, green, and blue because this is what the camera detects to begin with through the physical means, through the optics. Each of these different color spaces might be used in a different industry. So the color spaces that, or the color space that we use would be usually determined by the application that we're looking at. So we've got optical density, LAB, LCH. So optical density is very commonly used in printing applications, where we're looking at the differences in printed colors. So we have a sample here, a color sample here, where we have very slight variations of the same color or the same overall color as we perceive it, in this case a green color. Optical density will give us a cyan, magenta, and yellow values, and obviously also a total difference. So we're going to get a delta for each of the values. So cyan, delta magenta, and delta yellow, and an overall color difference. In this particular case, it's a Euclidean distance, just like we would do in RGB. So the distance in the three-dimensional space between the learned average color and the actual average color in the image. So of course RGB is the most commonly option used. It is a measure of the reflected light, and that's what we obtain. Optical density is it uses an inverse logarithmic scale to approximate changes in optical density, because optical density is a measure of the absorbed light as opposed to the reflected light. That's why the opposite basic colors are used. If you remember, at the very beginning of the presentation, we touched on these basic colors. We have red, green, and blue right here, but we have this magenta, cyan, magenta, and yellow. So in this case, the color space is very similar in shape. It's an orthogonal color space, but it's basically the absorbed colors rather than the reflected colors. LAB and LCH are different color spaces, usually represented by a color sphere, and we have a slide on that. This is basically a color sphere that's used for LAB and LCH. L in general is the luminance, the intensity of the object, and then we have two. In this particular case, if we look at LAB, we have two axes here, the A and the B, where here's the A. Positive A is red, negative A is towards green, positive B is towards yellow, negative B is towards blue. So an LAB value will be given, the A and the B value will be given by the color content, while the L value is more about intensity. The LCH, luminance, chroma, and intensity, will include, or hue, excuse me, luminance, color, and hue, will include, hue would be the angle here. So if we look at a slice of the sphere, the hue would be the angle between the two values there, the two axes. So it would give us an idea of the color content. So for example, in LAB, we have these two samples. Let's see, if the standard is our learned value, we have the sample, or the current sample, the current part. The difference between them will be reported. So you see it's a little brighter, so the L value is a little higher. So the delta L is greater than 0, is positive. A and B change a little bit. It's a negative change for A and a positive change for B. So if we go back here, it will change. So we have less of an A content, more than for a B content. So that change here would give us also an angle change, which will be the delta H if we were to use LCH instead of LAB. All right, so if we go back to Intellect here, I'm going to create a new product and bring up another sequence of images. Just part of what we just looked at in the slide presentation, just a little demonstration of how the tool is used. So if we go under flaw detection, color monitoring, we learn this color. Training section is very simple. You choose the color space. You can change, you can include a change in matte line and change the standard deviation. Changing the standard deviation, it's a way to differentiate between parts or not differentiate between parts that are very smooth versus parts that are porous, that are not very smooth, and that's because the standard deviation within a part that's not very smooth is going to be a little larger because of all the different changes in the surface. Basically, the way that the lighting is reflected because of that of the fact that the surface is not very smooth. So you can change that. Um, and as you see, the value that gets learned is the average red, green, and blue. And then we have a certain standard deviation, 0 in this case. If we move that down to this other value, we will see a change in RGB, and we see the color difference. Now in this case, we can change that color space to optical density, and we will get this CMY type of values. So we will see the delta change there. And we can pass and fail based on that difference. So we move it up. We see the color differences there is 0. So we can specify passing conditions for individual changes on those 3 values for the color space, or a maximum color difference. Say I want a maximum of 0.05. So there would be okay. And here it's going to fail because the absolute change is higher than 0.5. I can also match if I learned, let's say if I learned this color as a new color, it's going to tell me now that the closest color is C2. If this were a color monitoring or a color identification, rather a color identification application, and I were presented this part, and I knew or I was expecting color C1 all the time, I could set that up as well under a passing condition and fail when something other than that color content is presented to me. So right there is failing, and right here is passing. So that's where color identification comes into play by specifying a match color name or also color difference. And we can change that through a digital relearn. So if we change shifts, and now we're going to be looking at C2, I can change the expected color name by sending one of these digital relearn signals, and then on the next trigger, the next inspection, the camera would automatically switch between C1 and C2 and identify that, okay, now we want to look at C2 from now on until I change it again. We need to have C2 as our match color name. And that's color monitoring, very simple. In this case, this is not a way to move or exchange color information. You use pixel counting for that. Color monitoring is more for color identification type application, or color monitoring or identification. For cases where we have color various colors in the same part, and we want to identify between a part and the other, we can use the color identification tool. This is the third tool available for color applications. It's under the identification group, and it's used to identify objects based on color, based on percentages of various colors. So if we have a multicolored part, let's say a label, different colors, we want to identify, first of all, which colors are present and in what percentage those are present. So let's say we have a black and yellow part, and 80% of the part is black and 10% is yellow. And it's always like that. We want to verify that it's like that, then we can use the color identification tool for that. So in this case, we're looking at a part, so it's basically a part identification application based on strictly color. We're not looking at any patterns, edge-based or otherwise. We're just looking at color content of that part. And in this case, we're looking at a model or a label or part that contains multiple colors. The color ID tool itself does not learn the background color. If we specify this background color from another pixel counting, so let's say that we have a region of interest that takes up a label, but it also takes up the background of our label, or it spills over the part to a background that we don't want to take into consideration. Then we can use a pixel counting tool to learn that color, that background color, and eliminate it from the color identification process. In this case, color models again consist of multiple colors that get learned that are present at that point, and during the inspection mode, it will basically look at the actual color content and in what proportion those colors are present, and we'll try to match that with one of the learned models. Okay, the models that are learned through the color ID tool are actually system wide, which means that are available through different products and different sensors within the same product, or different sensors across multiple products. They can be renamed, deleted using a specific section of the System Explorer. So basically, that allows us to use the same models over different products or programs in our camera. This is the way it would look like in the System Explorer. Every time we learn the color model through any of the color ID tools, through any of the products in the camera, it will be put into the system level section that every other color ID tool will have access to. These are not shared for color monitoring or pixel counting tools. They're only available for color ID tools. Let's go back to Intellect and show you something like that. I'm going to use the actual camera for this. And let's say that we have a label like this for one of our cameras. This is one of our older cameras. I'm going to increase the exposure time here a little bit. Or a little too much. See some shadows here, so we're definitely not using the ideal lighting, but let's go ahead just for if we use a color ID tool here, let's learn this whole part. Now you notice that we actually have several colors present. Here we got white, we got black, we got blue, we got green. I'm going to call that color ID. Again, we can specify the background. If this extended towards the background, we can get rid of that by using a color that was learned by a pixel counting tool. We're not going to do that in this case. And in this case, we're just going to learn a color 1. And this is our color 1. This is our label. It's going to say 100%. And if we look at System Explorer here, under color models, and going to delete this previous test. And here's our color 1. If you look at color 1, it actually has various colors that were learned, right? With their individual average red, green, and blue values, and a certain color percentage. So color 0 is present as 50% of the part. Color 1, so if you look at color 0, the average red, green, and blue is about the same, and it's pretty low, so would assume that that is that black color in the back. We have 21% has a high average red and green color, so this could be that yellow color. And we also have this color here, color with higher percentages of all of them. So that with higher intensity levels of red, green, and blue is what I meant, and that's possibly the white color. So we have all the color represented there. Let's say that we have another label like this. Now it's giving me, now it has a different amount of all the different colors. In fact, the color green is not represented here. It's only black, yellow, and white, and it's in different proportions, all of them. So I'm getting a score of 70%. This score is based on how similar the parts are, how close this group of colors, this representation of colors with each of them on a different proportion or ratio, how close does that match to my previously learned color? And it's only 70%, so I'm going to choose a new model here. This is actually a different label, so I click OK. And now this one gives me 100% because it has the right ratio of each of those colors. If I open up the System Explorer, which I can go to our communication settings, but actually go to our color models. We go color 2. It actually only learned a single color that was pressed there. It's probably the black color. And now if I go back to the previous one, it's going to tell me that it's color 1. About 95%, that's based on the difference in position. Which brings us to another point. If we have something like this, we need to do position reference so that our region of interest of the tool is always in the right location where we learned it, so that if we have different colors that were learned in different ratios, we always get the same ratio of colors. In other words, if I move this a little bit, and now it's getting more maybe of the green than the previous white. Now it's only 86%, and so on. So we need to make sure that the area is pretty much consistent, so we get the same ratio of colors. Now it's 96%. So again, this color identification is a tool is for instances or applications where we have a part and we want to identify the part strictly based on the color content and the ratio of the different colors that are present. All right, so that was a very fast general overview of our 3 main color tools of the DVT product. with Intellect software. And just want to talk a little bit about the different applications um, where pixel counting will be used for obtaining color information that may be transferred to a different tool through a filter, but it could also be used for identification applications, classification applications, or even presence-absence applications. Color monitoring can be used for um, color identification um, or classification, and just strictly color monitoring, making sure that our main average color doesn't deviate much from what we learned. And color identification tools are used for application or in applications where we need to identify between parts that have a specific color content. The ratio of the color content is the same. Again, there is no pattern learning in this case. So in the case of the labels that we looked at, no pattern was learned there. Only the colors that were present and in the ratio in which they were present. So if there are no questions, we can finish here and invite you to our next online class on the Insight or DVT products. Thank you and good afternoon.